Alright, welcome to the fourth video covering this deep learning library we're building. So in the previous video we had already implemented the very basic architecture of gradient descent. So our network is ready and we should now test it before implementing more advanced updating algorithms or optimization algorithms such as Adam, momentum and etc. So in this video we are going to be creating this test file which will test this network with basic classification, binary classification and as well as regression problems. So we just need one more library here. I'm going to use SKlearn datasets to generate our own binary classification data. So just need this one more library. So it's very easy to install that. You should know how to install it. If you don't, then simple Google search will land you there. Then I'm going to import our library, this nn.py we have implemented, and then let's import numpy as np. Now let me just make this function def test run. And so first we are going to be running our binary classification problem. So let me just print this. Running a binary classification test. Yeah, right. Now we're going to use this SKlearn dataset library. So data is equal to datasets dot make classification. Oh sorry, it's a typo here. Yeah, so there are a few parameters you need to set, that is n samples, number of samples. I want 200 samples, and n features, which means the number of features the dataset should have. I'll set that to 10, and number of classes, so it is a binary classification problem, so I'll set number of classes to 2. Right, now let me just separate the data and the output. So the data, I'll denote data by capital X. So X is equal to data. So it's a list, and the first element is data, and then second element is the output. So I'm going to use transpose because remember in the first video I have already told that our network treats each column as a data set, not each row. So yeah, so this converts the row to column, and we've got our training data here, and the output I'll denote it by Y, and then let's transpose that too. So yeah, now let's configure our network. So net is equal to, we'll call our class nn.nn, and well, I have used this function nn dot to access this file nn, and then the class name itself is nn, so there's that. And let's call this its constructor. So I'm gonna use two layer neural network. So the first layer will definitely be input, and the input of the first layer is the number of features, so that's 10, and the hidden layer size should be 20, and the output of course should be 1 because it's 1 or 0. Now the activations I'm going to be using is for the second layer, which is the first hidden layer, I'm going to be using ReLU, and the last layer of course we're going to be using sigmoid because it's a classification problem. Right, now our network is ready, and let's just set our cost function to cross entropy loss. Now let's run gradient descent, net dot gradient descent, and let's set all the parameters. So the input is X and the output is Y. Alpha we're gonna be using somewhere around 0.01 or 0.05. that should suffice. Actually, 0.07 should also suffice. If it's not converging, we can try decreasing the value or increasing the value, but I think that's high enough. Now epoch, let's set it to 200, and print at should be equal to 5, but the default value here is self 5. We have already implemented in previous video. Where is it? Yeah, so we don't have to specify that. Alright, now let's calculate the output. So after running this command net.gradient descent, the network has already been trained, and the parameter values have already been stored. So let's just again calculate the output. So the output should be equal to net.forward with input. Yeah, and now let's just convert the output from probabilities to 0 or 1, which means 0 means the first class and 1 means the second class. So 1 into output greater than or equal to 0.5. So what this is doing is the sigmoid activation function, what it does is it calculates the probability. So it will be somewhere around somewhere ranging from 0 to 1, in between that. So if it's greater than 0.5, we'll guess the output should be 1. If it's less than 0.5, the output should be 0. So if the probability is more than 0.5, it belongs to class 1, and if the probability is less than 0.5, then it belongs to class 0. So there's that. Now let's just calculate the accuracy. Accuracy is equal to np.sum of output equals to y and divided by 200. So if output is equals to y, then it will be converted to 1, otherwise the value will remain to 0, and then we will sum all the times we have got 1. So that means all the time we have guessed the correct output, and then let's just print it. Accuracy is equal to accuracy into 100. So we will convert the accuracy to percentage accuracy, and let's just save it and try to run this and see if we have got any bugs here. Let me first clear, and then let's just try to run python 3 test.py, and oh, I forgot one crucial thing here. We have made this function, but we have not actually tried to run this. So yeah, if name equal to main, then let's run test run. Yeah, now let's run this again, and yes, so we've got this here, and as you can see the loss is decreasing with each step, and we've got an accuracy of about 94%. Let's run this again, and so as you can see accuracy has decreased, but don't worry, the network is working fine. It's just because we have used random initialization. So what we should do right here is make sure the random values generated is the same. So let's say np.random.seed, let's set this to 1, because we need the random values generated to be same, because if someone is trying to implement some other optimization algorithm, or someone is just updating the entire code base, and if they want to check if the network is working fine or not, so they can just use this file. But if it's random generation, then the network will output different results each time. So what this does is, using random.seed, is that it will make sure that all the random generated values are same. So the accuracy of the network should always be the same, no matter how many times you run this algorithm. So let me just test this again. So accuracy is 87.5, and let me just run this again. Again the accuracy will be 87.5, and all the losses will be same. So last loss is something like this, and you can just see here, and yeah, so it's same, right? And you can change this to any value from 1 to 3. It does not matter, the result will always remain the same. So that's it for this video, and in the next video we'll test this network for some regression values to make sure the entire network is working fine. And so stay tuned for the next one. Goodbye.